20 million years. And that is how long it would have taken the most powerful classical computers on Earth to solve the problem these scientists just cracked in 15 minutes. Not hours, not days, 15 minutes. In a basement lab in Denmark, a team of researchers just published a paper in the journal Science that proved, for the first time in history, a genuine, verified, no-debate quantum advantage. And what makes this moment different from every other quantum hype story you have heard before is one word: proven. Not simulated, not theoretical, not promised. Proven. Let's break down exactly what they did, why it changes everything, and what it means for the world you're going to live in for the rest of your life. Before we get into the experiment itself, you need to understand why scientists and engineers have been chasing something called quantum advantage for decades. Every time you search something on Google, stream a video, send a message, or do literally anything digital, a classical computer is doing the work. Classical computers processes information as bits, a 0 or a 1. At any given moment, every single bit in a classical computer is either off or on, 0 or 1, nothing in between. That binary logic has powered the entire digital revolution. It has put satellites in orbit, mapped the human genome, built the internet, and made your phone more powerful than the computers that sent Apollo 11 to the moon. But classical computers have a hard wall. When the problem gets complex enough, when the system you're trying to understand has enough variables, enough noise, enough interacting parts, the number of experiments or measurements you need to understand it grows exponentially. Not linearly, exponentially. Double the complexity of the system, and you do not double the number of measurements needed. You might need 1,000 times more, or 1,000,000,000,000 times more. At a certain point, the problem becomes physically impossible. Not impractical, impossible. You would need more time than the universe has existed. You would need more energy than the sun produces. The math just does not fit inside the physical world. That is the wall quantum computing was always supposed to break through. The theory goes back to physicist Richard Feynman in the 1980s, who pointed out that if you want to simulate quantum systems, you need a quantum simulator, a machine that speaks the same language as the universe at its most fundamental level. Quantum computers process information using qubits, which, unlike classical bits, can exist in a superposition of 0 and 1 simultaneously. They can be entangled, meaning 2 qubits become so deeply linked that measuring one instantly affects the other regardless of the distance between them. These properties, in theory, allow quantum systems to explore enormous numbers of possibilities simultaneously in ways that classical systems simply cannot. The problem is that for decades, quantum computing has been a technology of enormous promise and very limited delivery. Companies have built quantum processors, labs have announced milestones, headlines have screamed about breakthroughs. But rigorous scientists have always pushed back with the same uncomfortable question. Can you prove, mathematically and experimentally, that your quantum system did something that no classical system could possibly do in any reasonable amount of time? That proof, a genuine, certified, mathematically verified quantum advantage, has been the holy grail. And until September 25th, 2025, no photonic quantum system had ever delivered it. Here is what the team at the Technical University of Denmark actually did. The lead researcher is Professor Ulrik Lund Andersen, working with colleagues from the United States, Canada, and South Korea, all operating out of DTU's Center for Macroscopic Quantum States. The problem they chose to solve was characterizing the noise behavior of a complex quantum system, specifically what scientists call a bosonic random displacement channel. In plain language, imagine you have a system through which signals pass, and those signals get bumped around by random noise. Your job is to figure out the exact pattern and character of that noise so you can understand the system, predict its behavior, and eventually use it reliably. This is a task that comes up everywhere in real science, in quantum communication, in sensing, in machine learning, in building better quantum hardware. With a classical approach, figuring out this noise pattern requires an enormous number of individual measurements. You probe the system once, record the result, probe it again, record again, and repeat hundreds of billions of times. Because of the fundamental limits set by Heisenberg's uncertainty principle, the rule that says you cannot measure certain quantum properties simultaneously without disturbing them, each individual classical measurement gives you only a tiny amount of information about the system. As the system grows more complex, the number of measurements you need scales so badly that it becomes practically infinite. The team calculated that a classical approach applied to their specific system would require around 20 million years of continuous measurement to gather enough data to characterize the noise. 20 million years. That is longer than the entire existence of the human species by a factor of roughly 10. The quantum approach the DTU team used was built on entangled light, specifically what physicists call Einstein-Podolsky-Rosen states, or EPR states. Here's the setup. They created 2 beams of light and squeezed them, a precise quantum optical process that reduces the uncertainty in one property of the light beam at the cost of increasing uncertainty in another, like squeezing a balloon. When you squeeze two beams of light in a coordinated way, they become entangled. What happens to one beam is instantly correlated with what happens to the other, no matter what. One entangled beam was sent to probe the noisy system. The other was kept as a reference. Then both beams were measured together in a single joint measurement, one combined observation that captures information about both simultaneously. That joint measurement is where the magic happens. When you measure both beams together, the correlations built into their entanglement cancel out a massive portion of the measurement noise. Each trial of the experiment gives you an enormous amount of information compared to what any classical measurement could provide from the same system. You need far, far fewer repetitions to build up a complete picture. In the DTU experiment, the quantum strategy learned the behavior of the system completely in 15 minutes. The same task, attempted with classical methods on the same setup, would take 20 million years. That is a speed up of roughly 11.8 orders of magnitude, 11 and 8 decimal places. That number is not a rounding error. It is not an approximation. It is a gulf so vast it barely fits in human intuition. And critically, this was not just done in a sterile theoretical environment where everything was perfect. The experiment ran in the basement of DTU physics. It used standard optical components that you would find in a telecom laboratory. It ran at room temperature. It worked even with ordinary optical losses in the equipment, meaning the light beams were not perfectly preserved end to end, which is the real-world condition any practical technology has to contend with. Professor Anderson specifically pointed this out as one of the most important aspects of the result. The advantage comes from how you measure, not from having a perfect measuring device. The system is robust. It is scalable. It does not require exotic hardware that will take decades to build. It works now with equipment that exists today. The team also did something that separates this result from a lot of quantum computing announcements. They certified the advantage. They did not just run the experiment and declare victory. They built a mathematical proof demonstrating that no classical strategy, given the same number of measurements and the same experimental conditions, could ever match the performance of their quantum approach. The quantum strategy passed the certification bar with a success probability that is provably unattainable by any classical method operating under the same constraints. That certification is what makes this a genuine milestone rather than an impressive but arguable demonstration. Now here is where you need to sit with the implications for a moment, because the task the DTU team solved is not a party trick. Learning the noise pattern of a complex quantum system is a fundamental prerequisite for doing almost everything else useful with quantum technology. Before you can use a quantum device reliably, you have to understand its noise. Before you can build a quantum communication network, you have to understand how signals degrade in the channels. Before you can train a quantum machine learning model, you have to understand the system you are training on. The DTU experiment does not just show that quantum advantage is real. It shows that quantum advantage is available right now for a class of tasks that are directly relevant to building the entire quantum technology stack. Think about what this means for quantum sensing. Modern sensors, the devices that detect gravity waves, that map magnetic fields in the brain, that track tiny variations in acceleration for navigation, are already among the most precise instruments ever built. But they are limited by classical measurement noise. A quantum-enhanced sensor using the same principles the DTU team demonstrated could extract dramatically more information from the same physical signal with fewer measurements. That has implications for medical imaging, for detecting underground structures, for navigation systems that do not rely on GPS, for monitoring infrastructure, and for fundamental physics experiments that are currently impossible because the signals are too faint to measure classically. Think about what this means for quantum communication and quantum networks. The internet you use today relies on classical encryption, which is secure because certain mathematical problems are hard for classical computers to solve quickly. Quantum computers threaten that encryption, but quantum communication, using entanglement and quantum key distribution, offers security guaranteed by the laws of physics rather than the difficulty of math. Building reliable quantum communication networks requires understanding and characterizing the quantum channels those networks use. The DTU experiment just demonstrated a dramatically faster way to do exactly that characterization. Think about what this means for drug discovery into materials science. Understanding complex molecular systems, the behavior of proteins, the properties of new materials, the interactions between drug molecules and biological targets, requires modeling quantum mechanical systems. Classical computers struggle with this because quantum chemistry is inherently quantum. Characterizing the noise and behavior of quantum simulation platforms is a necessary step toward using those platforms to model molecules and materials. Every time the barrier to characterizing quantum systems drops, the timeline for quantum-assisted drug discovery and materials engineering shrinks. Think about what this means for machine learning and artificial intelligence. The current AI revolution runs on classical hardware, graphics processing units doing enormous amounts of linear algebra at very high speed. Quantum machine learning is a field exploring whether quantum systems can learn patterns in data faster or more efficiently than classical systems. The DTU experiment is, in a real sense, a quantum learning experiment. The system learned the behavior of a noisy channel exponentially faster than classical methods. The researchers themselves noted that their approach should help others identify areas where quantum learning advantage can apply. They specifically named machine learning as one of those areas. There is an honest caveat that the researchers themselves are clear about, and it is worth stating plainly. The DTU team has not yet targeted a specific real-world application with this technique. They built a proof of principle, a demonstration that quantum learning advantage is not just theoretical, but physically achievable with hardware that exists today. The gap between a proof of principle and a deployed technology is real and should not be dismissed. But the significance of what they demonstrated is precisely that it moves the conversation from quantum advantage might be possible in the future under ideal conditions to quantum advantage is real, proven, and achievable with off-the-shelf optical components in a university basement right now. Co-author Jonas Sko and Neergaard Nielsen, an associate professor at DTU Physics, said something that captures the moment perfectly. He noted that despite all the talk about quantum technology outperforming classical computers, the fact remains that up until this experiment, quantum systems genuinely did not outperform classical systems on any task that had been rigorously proven. That era is over. The first proven quantum learning advantage in a photonic system is now in the peer-reviewed literature in Science, the most prestigious scientific journal on Earth. The result has been independently verified. The math holds. The experiment is reproducible. What comes next is the translation phase, the period where a proven scientific principle becomes a working technology. History tells us this phase can be slow or fast, depending on how close the underlying hardware is to practical deployment. The fact that this experiment used standard telecom wavelength optical components is enormously significant here. The telecommunications industry has spent decades perfecting the manufacturing and deployment of exactly these types of optical systems. Fiber optic cables, optical modulators, photon detectors, optical amplifiers. The industrial base for this technology already exists at massive scale. That is a very different starting point than a technology that requires entirely new manufacturing processes or exotic materials that do not yet exist outside a research lab. The researchers said it themselves. Knowing that quantum advantage is possible with a straightforward optical setup should prompt other scientists and engineers to start looking for the specific real-world problems where this approach pays off. That is an invitation. It is an open door. And the scientific community is already walking through it. 20 million years of work, 15 minutes, in a basement with off-the-shelf parts, published in Science, certified by mathematics. The first proven quantum advantage for a photonic system in history. This is not the end of the quantum computing story. It is not the moment where everything changes overnight and classical computers become obsolete, but it is the moment the conversation definitively changes. From now on, the question is not whether quantum advantage is real. It is proven. The question now is how fast we can find every place it applies and how quickly we can build the technologies that will use it. The answer to that question will determine whether the next great technological revolution takes 10 years or 30, but the revolution itself, the question of whether it is coming, that question was answered in a basement in Denmark in 15 minutes.